have to say, well, when I make a measurement, typically it's not the quantity that I measure, but some quantity derived or calculated based on what I've measured. And so let's say that I measure X, but really the quantity of interest to me is W. And so obviously I have a recipe to convert X into W. So W is a function of X, well-specified function. And so if X is random, because I'm measuring it, W will also be random. And so then I can ask myself, okay, what is the expectation value of this quantity? And how does it relate to the expectation value of X? Before I talk about this, let's establish that if I measure X, it has its own PDF. And so when I translate X into W, this function, I will have now a modified PDF. So the PDF of W will be some PDF G of W. Obviously, when I carry out this integral, it will give me the expectation value, the mean of W, given the measurement that I carried out. And so, just to give you a few examples here, I give you a cubic box, and I say, what is the volume of the box? And so there's 6 of you in the room. We all take a ruler and we measure the size of the box. We all get a different value, and so we will all get different volumes for the box. In the context of other physical systems, if you measure the temperature, you can use the temperature to determine the energy of the system, Stephen's law. And so the temperature measurement being a random outcome, it will give you some random outcome of what the energy is, and so on. The question arises, how do I convert the density, the PDF of X into a PDF for W? The answer is here. And the answer relies on the notion that when I have a measurement, I have an event. And so when I measure this event is then some subset of the sample space of X. That event will be in a different subset of the subsample of W, but there's a one-to-one correspondence between the two subsets. So this is the sample space of X. This is the sample space of W. This is the relationship between W and X, some arbitrary function. And so I'm asking, what is the probability of measuring within this interval that will map one-to-one to a value in this interval? And obviously, dx and dw don't have necessarily the same value. But at the end of the day, if I cover the right interval W, I will have a one-to-one. So the probability of having one event here will be the same probability of having the event in that interval. So that defines a one-to-one. And so at the end of the day, then you can convince yourself that the expectation value of W is going to be a convolution integral of the expectation value of X times the value of W given X, integrated over the range of interest. And so now we can introduce a few more quantities of interest that we deal with in physics all the time. The first set of such quantities is what we call moments, sometimes called algebraic moments or simply moments. The moments are basically the expectation value of some power n of the value of x. Right? So instead of taking the average of x, I'm taking the average of some power n of x. Obviously, for n equal 1, that's the mean that we just talked about. There's also the notion of centered moments, or moments relative to the mean. And so then I can take the expectation value of x minus the mean to some power. And so that will be the integral of x minus mu, the mean, to some power, fx dx. This is something that I'm sure you have seen before. example of this is for n equal 2, and so at x minus the mean to the power 2, that is the average of x minus the mean to the power 2. We typically call that sigma squared. That's the variance. Now you can expand the parenthesis here. That will be x squared minus 2x mu plus mu squared. You can verify very easily that this will simplify to this expression. So you will find that sigma squared, the variance, is simply the second moment minus the square of the mean. So what do you do with this? Obviously, if you have a PDF such that x has a very large probability of being far away from mu, right? So if this f of x here is very broad, for instance, the green line here, then contribution to this integral will be finite for large values of x, and because there's a square, you will be summing large numbers and varying such large numbers, so the variance will be large. If the PDF is very narrow, so let's say the black curve, as soon as x is far from the mean, the contribution to the integral will be essentially vanishing, so the variance will be small. And so this then becomes a measure of how broad or wide this distribution is. So that's the variance, and the square root of the variance is known as standard deviation. We can also define standardized moment, where you would take some centered moment k divided by sigma and part k, but that's just not very interesting for now. Sometimes used in heavy ion physics, not so much in particle physics, a notion of skewness and kurtosis. Skewness and kurtosis have been measured quite a bit in the context of the beam energy scan at Brookhaven National Lab for connecting measurements of fluctuation with susceptibilities of the coronal plasma. And so these are defined as centered moment. So the skewness is this third centered moment divided by the third power of the standard deviation. And the kurtosis is defined as the fourth centered moment divided by the fourth power of the standard deviation. And what this says, so for the kurtosis, for the skewness, if you have a distribution that is asymmetric, it will tell you whether it's leaning to the left or leaning to the right. And so if you have a PDF that is not symmetric, then the skewness will be non-zero. And the kurtosis, on the other hand, tells you not how narrow the distribution, but how stubby the distribution is, or how much tail it has. Now, this is quite, so far, you can do a lot with the concept we've seen, but in the context of heavy ion physics or modern particle physics, it's not very useful or sufficient because in general we're not measuring just one variable, we tend to measure many variables at the same time. So oftentimes we want to know how these different variables are connected or correlated with one another. To introduce this type of correlation, we need to introduce the notion of multivariate function, which is just a PDF for many variables. And so we can do this with two variables, x and y. And so now the PDF becomes a function of x and y, which I can express as an amplitude out of the page here. And so this PDF now tells me the probability of finding two events simultaneously. So I have an event within x, an event within y. An example of this would be, okay, I have collision produce two particles. What is the probability of finding the first particle in a certain momentum range, let's say between 10 and 20 MeV, in finding the second particle between 30 and 40 MeV. It's a little contrived, but you can ask yourself, what is the probability of observing these two things at the same time? Well, you can slide the momentum range, and so that will give you a momentum range for the first particle, momentum range for the second particle. And you can ask, in each momentum range, what is the probability of finding the particles in these momentum ranges? And so that's really the probability of finding two events simultaneously. That's called joint probability. And that means that x will be within this interval and y will be in that interval. And I will describe this with a probability density, which is a function of x and y times the x and y. I can extend this to an arbitrary number of variables by just redefining it like this. So now I can start talking about actual measurements. Let's say that I am carrying a measurement, and I carry this measurement n times. I will have n values for the quantity x. This could be the same measurement repeated n times, or it could be n different measurements of different quantities. It doesn't matter. And so the function now, the multivariate function of the vector x, this whole thing will be, I can ask what is the probability of measuring a certain value of x1, value of x2, x3, and so on, all the way to xn. And so that will mean, what is the probability of measuring x1 being in the range x1 to x1 plus dx1, x2 in the range x2 plus x2, x2 up to x2 plus dx2, and so on and so forth. And so that is going to be the probability of finding this particular set of numbers, or this combination of numbers, will be just this expression, where now this is a multivariate density function. Okay? And of course, if I sum all variables x1, x2, x3, and so forth, if I span the entire space of n dimension, I will recover unity. So sometimes we measure a large number of variables, but we don't want to deal with all those variables. Case in point, in heavy ion physics, within the acceptance of our detector, we can see 6,000 particles. Lead-lead collision produce 6,000 particles. 6,000 particles, each of them have px, py, pz, 3 coordinates of momentum. That means I have 3 times 6,000 variables in my system. Can I visualize that in my head or in a piece of paper? Hell no. So I'm going to try to reduce the amount of information that I'm dealing with. The way I reduce this information is by summing probabilities on quantities that I'm not interested in. Physicists call this averaging out quantities that are not of interest. Statisticians call this marginalization. You put to the margin those quantities that you're not interested in. Either way, in practice, that amounts to summing or integrating over all these things that you're not really looking at. And so suppose, to keep it simple, suppose I'm measuring two quantities, x and y. And I've done this measurement already, but I'm not so much interested in the value of y, but I'm interested in the value of x and how x is distributed. And so I can then sum all values, the density of over all values of y. And so that will give me the probability of x irrespective of the probability of y. And so this is known as the marginal probability of x irrespective of the other values of y in particular. And so that will be the probability of that event, finding a certain value of x irrespective of y, when we started with a PDF having a dependency on two variables. And so the notation I use is f of x, f sub x of x. So this is called the marginal PDF for x. And so in practice, when you're dealing with functions, that's going to be an integral of the density over all values of y. Of course, I can flip the roles. I can say I'm interested in the value of y, and so I'm interested in the PDF of y, irrespective of the value of x. So that's going to be an integral over all values of x. So that's known as the marginal PDF for y. Let me give you an example of what I mean here. And so I have value of x, values of y. I have isocontours of f of xy. F of xy is the joint PDF of x and y. You can see that I have contours that are slanted, and so this tells me that when I have large values of x, I have small values of y, and when I have smaller values of x, I have large values of y. And so what are those marginals here? If I integrate all values of of x, so I have this PDF, and I integrate over all values of x, I'm going to get a function which is a function of y, and that's what I have here. So I get a density which is a function of y. If I now integrate over all values of y, I will get a function of x, and that's what I have here. And obviously, this function and that function can be very, very different because they mean different things. Okay. An example of this would be I'm measuring the height and the weight of particles, of people. Okay. So let me get, I'm going to indulge with self-deprecating humor. So if you live in Europe, the height of a person and the weight of a person are closely related like this. Okay? That means that we're made of matter. If I'm taller, I tend to be heavier. But if you live in the United States, where I live, at a given height, you can be normal or really obese. So in the United States, the distribution goes like this, where you have, at a given height, you have a normal, but you also have a tail of very heavy people. And so that's the notion of what a joint PDF is. And of course now I can project this PDF on the height axis, or I can project it on the weight axis, and I will get different distribution. Okay. So now I can ask a more interesting question. So, and enters the notion of conditional PDF. And so what we've seen earlier is that I can ask, what is the probability of finding events in the intersection of two subsets and divide by the intersection of subset A, and that gives me the probability of B, event B, given that I know event A has taken place. By virtue of what I just defined, this probability of the intersection is a bivariate PDF, and I divide by the marginal distribution for x. And so that is known as obviously when I do this, here I have dx dy, and I have dx here, so the dx simplify and I'm left with dy. That's a probability. If I now think in terms of density, I remove the dy and I'm left with this ratio only. So this ratio is known as a conditional PDF. It says the density of seeing y given x is just a ratio of the density of xy divided by the marginal of x. So that's a conditional PDF of y given x. Obviously, I can flip the roles and I can have conditional PDF of x given y where I flip the roles. here's an example of how this works, and seeing how interesting this can be. Picture my example again, height versus weight. The correlation here is, well, the example doesn't work because here there's obviously a correlation, a positive correlation. Here I have a negative correlation, and we'll define it in a moment. I can ask, what is the probability of x, the function of x, given different values of y? And so if I choose this range of y, and I integrate all values of the PDF, the bivariate PDF in this range, I will get the solid curve. If instead I integrate within this range, I will get a distribution which is a little bit to the left, and that's the dashed line. And so that's the notion of conditional PDF. Knowing that I've made a certain measurement of y, what is the density of probability of measuring x? So again, I'm trying to build up to talk about correlation function in the third lecture. So the really important thing here is the notion of statistical independence. And so we saw that the notion of statistical independence is defined as the probability of measuring an event in the intersection of two subsets being equal to the probability of the event being in each subset. And so in the context of conditional and marginal probabilities, that will mean that the joint probability of x and y, the joint PDF of x and y, it will be equal to the marginal for x and the marginal for y. It's just a product. Having done that, I can ask now, what is the conditional density, conditional PDF of x given y? And so that is defined as the joint by the marginal. And so the joint now being the product of the two marginal. And so I have f sub x, f sub y divided by f sub y. Obviously, the f sub y is simplified, and I end up with f sub x. And so what this says is that when I have statistical independence, the conditional is equal to the marginal, and vice versa for y. Let's get back now to the notion of function of variables that are random variables. So I measure x. It has a certain PDF of x, and now I want to connect x to some other variable or observable a. So I have some function a of x. If x is a random variable, a is also a random variable, and I will call g of a the PDF of a. And so I have a certain PDF for x, and I'm asking myself, what is going to be the PDF of a? Okay? And so we saw already that by construction I have to sum all the values of x that will map onto some range of a. And so that's what I wrote here. All values of x that are mapped in a certain interval ds will map onto a, and that's what I have here. In practice, if I have a single variable, it means that I'm going to sum or integrate from x of a to x of a plus dA. And that's going to be how I calculate the density GA. Now, this range of integration really is just an infinitesimal range of integration, so you can easily convince yourself that G of A then is f of x of A times the absolute value of this derivative. Right? Obviously, we take an absolute value here because we're dealing with positive definite quantities. Let me give you an example. Let's say that a of x is some parabola, right? X squared. The inverse will be plus minus square root of a. The derivative will be 1 over twice the square root of a. And so now I have measured x. I want to infer what a is. And so given x, well, x could be positive or negative, and both will give me some value of a. So given the two roots have equal contribution, when I calculate g of a, I must multiply by 2. Two ways of getting the same value of a. And so 2 ways of getting the same value of a. So that's f of xa times the dx dA. And the two roots have the same derivative. So I end up with, I had a factor of 2 here, canceled by this factor of 2. So I end up with g of a being the f of x of a divided by the square root of a. That's how I can map the PDF of one variable into another. That's just a brief example of how this can be done. If you have many more variables, if now I have a joint PDF of many variables, x1, x2, and all the way to x10, then I must sum over all the possibilities. What does that mean in practice? A now is going to be assumed to be some function of x1, x2, x3, and so on. And so effectively now I will have a surface A will be an hypersurface in a space of n dimension, and I must sum all the values of x1, x2, and so on. That will give me values of A in that certain interval of dA. And so in practice, this can be a fairly complicated integral. In practice, I'll give you a couple examples of how this can be done. If I now have two variables x and y, each distributed with their own known PDF, g of x and h of y, let's calculate the probability density of some variable z, which is a function of x and y. Right? And so in this example, the probability of x and the probability of y are independent, statistically independent. X has a probability of PDF g, and y has a probability of PDF y. So the probability of z will depend on the product of these two values, x and y. Right? And so now it depends what z is. So let's say z would be the product of x and y. And so to know the probability density of z, I would have to sum over all values of x and y that are going to give me a certain value of z. And so that's going to be the integral of the probability of x times the probability of y integrated such that I get a certain value of z. In practice, I can do this as follows. Obviously I have to integrate over all values of x, all values of y, such that I will have a certain value of z. Because I have statistical independence, I can factorize the two integrations. So I have integration over x, integration over y. Obviously, they're not completely independent of one another because now I have to respect boundaries. And so at the end of the day, I'm not going to, since you can access this slide later, I'll just give you the results, is that the probability density of z will be the probability of this integral of g of x times h of z over x. Right? Because I have z must be equal to x of y times y, so this here is the probability of y, and so y is the probability of z over x. And I have this variable here, 1 over x. So that's an example of how you can integrate and find the probability density of a function. Another example would be if now z would be the sum of two variables. Again, I must sum over all values of x and all values of y. Now I'm going to use a different way of doing this. I'm going to say, okay, I'm going to do the sum over all values of y and x. I'm going to impose that z must be the sum of x and y. I can do this with a delta function. And so with this technique, then it's very trivial to see that f of z will be just g of x, the integral of g of x times the integral of z minus x. So this is something that we encounter quite a bit in measurements. Now that I have a function a of x, I can ask what is the expectation value of that function. And so that if I knew the PDF of a, that would be, this expression would be the expectation value of a, just the average. Now I can go back here and say, okay, the density of a is given by this integral, so I'm going to use this integral now. And so I'm going to sum over all values of x1, x2, and all the way to xn. When I have this value, when I have all these values of x1, x2, it gives me some value of a. And the density of that a will be determined by the density of x1, x2, and so on. So the mean of a will be given by this expression. Okay? And this can be, a can be arbitrarily complicated. In practice, let's discuss some very simple examples of this. So let's say that I have a measurement involving many variables, x1, x2, x3, all the way to xn, but I'm interested in the mean of x, let's say x1 or x2. So I'm going to be interested in the mean of the variable number I, index I. And so that becomes the expectation value of this variable. And obviously it has to be equal to the mean of that variable. I can ask, the next thing I can ask is, well, what is the variance of this quantity? The variance, as we saw a moment ago, is the expectation value of the value of the variable minus its mean to the power of 2. And so that's going to be an integral over x1, x2, and so on, of the density, f of x, times the square of a minus the mean. And so that's the variance of a in general. If I now select a to be just one variable, x sub I, then I will have an integral over all values of x, of x1, of x2, and so on. And I will have the square here. Now what you can visualize, which I haven't done on the slide, if for simplification here, if this is, let's say that I could factorize this and this. Then you can easily convince yourself that this integral, now, which is very complicated in principle, now will have to become a very simple integral. And so on. But one of these integrals will have this factor. And so the factor could be here, let's say. And then it's quite clear that this integral will give me unity. This integral will give me unity. All the others integral will give me unity, except for this one, which is the variance of x. Okay. Now, here, to do the example, I simplify by factorizing this into products. But even if I don't factorize, the notion still holds that what I'm getting is really the variance of x2. And that's given by this expression. Now, and this is where we're going again with this building up to steady correlation functions in physics. I can now introduce the notion of centered moments. And so the centered moment of two variables, the product of two variables, x sub I and x sub j, x1, x2, or y and x. And I will define what is known as the covariance, a quantity that you're probably familiar with. The covariance of x sub I and x sub j is going to be the expectation value of the product of x sub I minus the mean of x sub I, x sub j minus the mean of x sub j. And again, that's simply this expectation value, this integral here, of this difference times the density. Okay. So an example with two variables only would be the covariance of x and y is going to be the difference relative to the mean of x, the difference relative to the mean of y times the PDF of xy. And you can, if you think about it for 2 seconds, you can convince yourself that this is in general going to be equal to the mean of xy minus the product of the means. Okay. And so now, in general, the covariance can be a positive, null, or a negative quantity. If this integral is larger than the product of the mean, the covariance is positive. If this quantity is less than the product of the mean, the covariance is negative. And if this integral is equal exactly to the product, then the covariance is 0. And so if the covariance, so as I said, if this integral is exactly equal to the product of the mean, then I can infer that there's a chance that this factorization applies. And so if the covariance is 0, it could mean that x and y are statistically invariant, independent. It's not guaranteed, but in general, it will work. Okay? So it means that if the covariance is 0, there's a big chance that the two variables are statistically independent. Let me illustrate this maybe a little better. I'll give you examples. I have here the PDF of x and y plotted in different conditions. So here I have a condition where these are circular contours. And so the covariance here is 0. Given, if you know the value of x, it really tells you nothing about the value of y. Likewise here, the covariance is still 0, but x has a larger variance than y. In this case as well, now x has a small variance, but y has a large variance, but they're basically independent of one another. So these three cases have 0 covariance. In this case, D, you can tell that as x increases, there's the probability is such that y will also be increasing. So you have this slanted contours, set of contours, and so this means that when x means that if this is large and positive, this will also have a tendency to be large. Right? You're sampling this, so when you have high probability of being here, when x is large, so y is also large. When x is small, y is small. So that gives us a correlation. X is really correlated to y and vice versa. And so that gives us a positive covariance. In this example here, I have a set of contours that is slanted this way. And so now when x is large, y has a tendency to be small. And when x is small, y has a tendency to be large. And so that gives me a negative covariance. And of course, if the correlation is nearly perfect, if y is almost equal to y, if the two variables are nearly equal to one another, then you have a nearly perfect correlation. Mathematically, it's convenient to introduce the notion of covariance matrix. So I've talked about variance and covariance. I can rewrite this in a more generic way. X sub I minus its mean, x sub g minus its mean. If I and j are different, then I have a covariance. If I and j are the same, I have a variance. And so this altogether defines a covariance matrix, and you can verify very easily that you can interchange I and J, and the values are going to be the same by construction. And so it's so this defines a so-called symmetric matrix, and we can use this matrix in the context of many, many analyses. And I'll give you some examples in the next lecture. Another quantity that is often of interest is the so-called Pearson correlation coefficient, where now we take the ratio of the covariance by the product of the standard deviation. And so why would we do that? So obviously, if I go back here, let's say here, how would I, so here the covariance is 0 in all cases, but you can tell that in this case the variance of y is large, here in this case the variance of y is small. If I have a correlation between the two, such as here, these two now are correlated, how big is this, how strong is this correlation? So in order to quantify this correlation, I can normalize to the variance, the standard deviation of each of the variables. And that's what I've done here with the introduction, of this so-called Pearson coefficient. If you pay attention to this in detail, you can convince yourself that this coefficient cannot be larger than 1, and it cannot be smaller than -1. And so it is bound in a range from -1 to 1. If it equals 1, that means you have a perfect correlation, you have a linear correlation. And if it's -1, you also have a perfect correlation, but it's anti-linear. And so this is used quite a bit in statistics to understand what is the relationship between two variables and how tightly two variables might be correlated. How much time do we have?
12 o'clock would be the...
12 o'clock, okay, so I can cover maybe one more topic or two. So let's talk about uncertainties and errors. Now that I've spoken about PDFs, I've spoken about correlations, we can talk about uncertainties in measurements. Everything that I've done so far is to talk about, in a somewhat abstract way, about PDFs, but these PDFs really represent the outcome of a measurement. I'm measuring the value x. How is x distributed? What is the PDF of x? I'm measuring a variable y. What is the PDF of y? How is y distributed? How x and y are distributed is really the outcome of the measurement. And if your measurement, well, if x and y are very specific numbers, say the speed of light or the mass of hydrogen, you're going to get random values that hopefully, if your measurement is well done, should be close to the actual speed of light or the mass of hydrogen, but they're not going to be perfectly equal to the mass. You're going to have some dispersion, some variation or some fluctuations. And so enters the notion of experimental error when you carry out the measurement. And so, so let's say that I'm carrying out a measurement, and I'm carrying out a measurement of some quantity, x, and I do it n times. Let's say, so when I do this, this measurement will have some PDF, right? It will be a joint PDF of the probability of measuring all these variables. I'm going to call this f of x vector. If the PDF is known, in principle, I could compute ad initio the mean, the variance of all these variables. That would be nice. In practice, it may not be known. In practice, I may not know the PDF of the joint PDF of these variables. In general, we don't know what the PDF is. However, I can measure averages of some of these quantities or variances of these quantities. So let's assume that I have made this measurement, and now I have the mean for value x1, value x2, and so on. Let's also assume that I have the covariance of x1 and x2, x1 and x3, and so on and so forth. And so let's say that I have a covariance matrix of V sub ij. And so now I've made this measurement, and based on these variables, I'm going to be calculating some physical quantity of interest. Right? So let's say the quantity of interest is y, and y now is a function of all these variables that I've measured. Because x, when I measure x1, x2, x3, and so on, fluctuate, that is, they're a random variable, y is also a random variable. And I'm interested in understanding what is the limitation of the precision I have, given that each of the random variables, x1, x2, and so on, have their own fluctuations. So how can I understand the variation of y, given that there are variation on x1, x2, and so on? It seems like an impossible problem if I don't know the PDF. But it's not. It's actually solvable. So what I'm going to assume here is that I know this function, obviously. I need to be able to calculate y given the values of x, 1, x2, and so on. And provided that I can, at least in principle, do an integration of this PDF, I will be able to get some values of uncertainties on y. And I'll show you why and how. When I do this measurement, I might be interested in knowing what is the average value of y that I'm going to be seeing, and what is going to be the variance of y. Okay. If I knew the PDF of x1, x2, x3, I could calculate it. But I don't know the PDF, so I'm going to find another way to do this. And so the trick then is to do a Taylor expansion of the function y as a function of x. And so I'm going to do this Taylor expansion relative to the mean of each of the x1, x2, and so on. And so I can do a Taylor expansion of y of x relative to y of mu. And obviously, to do this as a Taylor expansion, I have to add this second term, where now I have the sum over all possible ways of x, x1, x2, and so on changing relative to one another. So I'm going to sum dy dx sub I times the product of times x minus its mean. And I'm going to truncate the series here. For this, it's good enough. Now I'm interested in the expectation value of y, and so I'm going to calculate the expectation of y. Now, the expectation value, so this here is just a number, right? And so I will have at least this term. Now, the derivatives here, this y is a specific function of x, 1, x2, and so on, and so the derivatives are just numbers. The expectation value these numbers can be factorized out of the expectation value. So this here will be so if I take the expectation value of this sum, this expectation value, I can rewrite it as a sum. So this is an expectation value is an integral. An integral will commute with a sum. This is just a number, so I can take it out of the sum, or the expectation value. And I have then this the expectation value of this term then is equal to the sum of the expectation values of these guys. But mu sub I is in fact the expectation value of x sub I. And so this vanishes by construction. And so then when I seek the expectation value of a function of several variables, it is just the value of the function at the value of the mean of these variables. Okay, so what about the dispersion of y? And so now I can calculate the expectation value of the square of y. I'm going to do this again as a Taylor extension. And so I'm going to have the first term evaluated at mu. I'm going to have a second term involving first derivatives as before. And then you will see that this, well, obviously we just saw that this is vanishing. So this expectation being vanishing, to get something interesting, I have to go to the next order. The next order will be the product of y by itself. So this is y. So I have a Taylor extension of the first term of y by y. And again here, I can commute the sums and the expectation values. So the sums are going to come out. These derivatives are simple numbers, so they're going to be here out of the expectation value. And now this is then the expectation value of the product of these two differences, and you will recognize this as the covariance of x sub j and x sub I, which I can now represent as a covariance matrix. And so this is a result that you may not be aware, but you've been using this result in all your experiments, if you have been doing the experiments. So now if I subtract, in order to get the variance of y, right, to get the variance of y, I'm calculating the expectation value of the square of y minus the expectation value of y to the power 2. And so with this, we've established that it's the mean of y, and so that's going to be the power 2. And then this we just found an expression which is y squared minus this sum. And so this square will be canceled by this square. And so I end up with only this second term. The second term tells you what is the variance of y given the variance of x1, x2, and so on and so forth. This formula you have used already in a simplified way. Oops, I'm going in the wrong direction, sorry. Let me give you a couple examples and then we can start. Let's say that I have a function of y, which is just the sum of two variables, x1 and x2. Obviously, the derivative of y and x1 and x2 are just 1, right? And so the variance of y will now have three terms in principle. Product of derivatives relative to x1 squared times the covariance of 1 with itself. That's the variance of 1. Same thing for x2. And then you have a so-called cross term, dy dx1, dy dx2, evaluated at the mean, times the covariance of variables 1 and 2, and then times the covariance of variable 2 and 1. These are the same. The derivatives are also the same in this case, not always, but in this case they are. And so this expression then simplifies to the variance of y is going to be the covariance, the variance of the first variable plus the variance of the second variable times the covariance between the two. This expression you've seen before, I'm sure, without this term. In general, this term is omitted in undergraduate texts. in measurements that we carry out in particle physics, it's often the case that x and y are very strongly correlated. If the correlation is negative, then you can realize that if this is negative, then the error will be small. The actual error on a measurement would be much smaller than just the first two terms together. I just said error. When you measure x, you have fluctuation. These are the fluctuations of x. These are the fluctuations of y. Consequently, the fluctuations of, first variable, second variable, the fluctuations of y are this. And so if you repeat the same measurement, you would see that y fluctuates according to this expression. So if you don't include the covariance, and the covariance happens to be negative, you might very much overestimate the error on your measurement. You've seen also this formula. If now I think if the quantity y is the product of two variables, x1 and x2, now I take the derivatives, right? So the derivative relative to the first one is x2, the second one is x1. I apply the same generic formula once again, and now what I find is that the variance of y has this more complicated appearance. But now if you apply it, you say, well, let's divide by the square of y. So that's dividing by the square of the product. And so when you do this, you'll see that some of these terms are actually canceling out, and you will get this very simple formula where the relative error square will now be the sum of the relative error for the first variable, the second variable, and then you'll have a covariance term. Okay, so at the end of the day, the variance of y divided by its square is equal to the variance of y divided by its square plus the variance of x2 divided by its square, and the third term, the covariance. Again, if you have a negative covariance, if the two quantities are really related to one another or anti-correlated, then this error can be very large or very small, much smaller than what you would deduce if the two were independent. And so in general, if you want to do advanced measurements, you have to take that into account.